Hi, this is Sue McBride, and today we are going to be looking at section 2.2, dealing with errors from the textbook Statistical Reasoning for Everyday Life. In this PowerPoint, we're going to continue with our course goal of using the vocabulary for statistics correctly, and you've done quite a bit already, so make sure you're reviewing sections chapter 1 and 2 that we've done so far for all the vocabulary. Again, statistics is all about understanding what you're asking and what you're reading and seeing, so the vocabulary is rather critical. So today we're going to be focusing on vocabulary dealing with errors, and actually do a little bit of a computation, so you'll want to have a calculator handy. So we're going to be discussing the difference between random and systematic errors, as well as be able to describe errors by their absolute and relative sizes, plus know the difference between the two terms accuracy and precision. They sound like they're alike, but in statistics they are slightly different. Alright, let's see. So we're going to start with random versus systematic types of errors. These are things that can occur as you're gathering your measurements. So a random error is just one that occurs because of random and inherently unpredictable events in that measurement process. There's no way you can plan for it. It's just going to be totally random and totally unpredictable. So hence it gets the name random errors. Systematic though, systematic sounds like it's occurring all the time, which is exactly how we define a systematic error. It's one that affects all the measurements in exactly the same way. So let's look at a few examples of that. So here, if I have a scale that measures differently, it's consistently off, so that is going to be a systematic error, and you can fix it by recalibrating. So a calibration error is one that would be a classic systematic error. We'll look at that again in a second when we're talking about putting babies on a scale. You can test a calibration by using known weights. So those are things that you can do to make sure the scale gives what you're expecting. So you have known weights. Now that's interesting is, well, how do you know the known weight is also the correct weight? So you can get yourself going in a vicious cycle. But usually in a science classroom, you've got little weights that you know are correct because they've been tested against other known ones. So there you go. Alright, so calibrating your scale correctly can help take care of at least that systematic error. Okay, so here we got the baby getting weighed. This is in your textbook if you want to get a fuller explanation, but if anybody's ever put a baby on a scale, they squirm around quite a bit. So here you would get random errors. If the baby happens to hold very still, you might get one reading, where if they're wiggling around, you'll get slightly different. So anywhere, as your book says, between 14.5 and a 15-pound baby. But there's nothing you can do to fix that. It's just totally random. Conversely, the scale, you find out later, reads 1.2 pounds when it's empty. So hence, that's going to be a systematic error, because everything that's weighed on there is going to be exactly 1.2 pounds off from what it should have been, too high. So you can adjust for that systematic error by just taking all the measurements you took that day and subtracting 1.2. So that way you know that systematically everything was the same. So random, you can't predict it. Systematic, it happens exactly the same every time. So if you go to the web and look at the current time, now I do this all the time. How far off is your clock or watch? Describe those possible sources of random and systematic errors in your timekeeping. So as I'm sitting here making this PowerPoint, my computer tells me it's 9:45, but my clock tells me it's 9:47, and if I go out to my car and look at my cell phone, those are two more that are all slightly off. I can never seem to get all four saying exactly the same thing at exactly the same time. So that's going to be a random error, and nothing I can do about it. But once I know one clock is off by this much every time systematic, then I can adjust it. So systematic versus random, and yeah, the clocks are a real issue. All right, let's talk about global warming data. We know that they've been talking about this for quite a while because they want to know how much the average temperature on the entire Earth has been changing over time. That's called your global average temperature. Now, two difficulties you can run into trying to interpret historical temperature data. If you've ever thought about it, they didn't even start taking temperatures for a long, long time. The thermometer didn't exist. So when they first started, they were very simple measuring instruments, and they're recorded by hand. Also, the second thing, most temperature measurements were recorded in or near urban areas, which tend to be slightly warmer than the surrounding rural areas. Like I live here in Richmond, but my friends live out in Goochland, and it's always colder out there than it is here in the city. So how do these two difficulties produce random or systematic errors, and what would be the implication of the errors? All right, so the first difficulty, because people were making those errors occasionally reading and writing, those would be random. Can't predict it, could be a little high, could be a little low, but one of the things you can do then is if there's several readings for the same region for the same day, you can average those and use that number to minimize the effect of a random error. Now, a systematic error, because that heat is a little bit higher in the urban than in the rural, is just something we can estimate how much it might be off and correct that way by comparing the rural to the urban and figure out, oh, this is always this much higher. So systematic, you're looking for something that happens all the time. It's consistent. Random, you're looking for something that happens on a case-by-case basis and something strange or unknowable could happen. Now, the fact that urban areas tend to be warmer than they would be in the absence of human activity has a name. It's called the urban heat island effect. I think that's kind of interesting. Major causes of this could be related to things like burning fuel in automobiles, homes, and industry. And to me, one of the big things they mention here is the pavement in large masonry buildings. You know, when you go outside and walk through the parking lot of the store, that whole parking lot area is so much hotter because of the concrete and the cars and everything like that. They tend to retain the heat and also retain the heat of the car engine. So, you know, if you look at a thermal image, you can definitely tell where the big cities are. All right, next type of error, absolute versus relative. This is the one you're going to need your calculator for. So if you need to pause and go get one, please do. Just to, remember, you need to have a graphing calculator for this class. So go get that and practice learning it here. All right, so absolute error describes how far, and in math we measure how far by subtracting, how far a claimed or measured value lies from the true value. So you've got what you're measuring, you've got what is true. If you subtract those two, you'll get the absolute error. The order you want to subtract in is the measurement you took minus what you know the true value is. A relative error, conversely, compares the size of the absolute error, which you have to compute first, to the true value. It's often expressed as a percentage, and this is the way you'll hear it in news reports, etc. So my relative error I would find by finding the absolute error first, so that's going to be in the numerator, and I'm going to divide by that true value in the denominator, and then I'll multiply by 100 to get it into percents. So when you divide absolute by true, you'll get a decimal. When you multiply it by 100, you'll move it over 2 decimal places. Then you do your rounding from there. So whenever you're rounding percents, make sure you move it over the 2 decimal places first and then round. All right, so for example, we have a true weight is 100 pounds. Well, that would be a child, but the scale says you weigh 105. So your absolute error is going to be what you measured, the 105, minus the true, which is 100, or a 5-pound positive absolute error. So if your measured value is bigger than your true value, it will come out positive. If that absolute error is positive, then your relative error will also be positive. So we'll take our absolute error of 5, divide it by the true value, which was 100, and if you pop that into your calculator, it will say 0.05. Then I have to move it over 2 places to get my 5%. There was no decimals after it, and we'll talk about that with accuracy and precision in just a moment. All right, so accuracy and precision. Sometimes these terms are used interchangeably, but not in statistics. And in science as well, actually. So when we define accuracy, that's how closely the measurement approximates the true value. Close is generally defined as a small relative error rather than a small absolute error. So when they're talking about this is accurate to 5%, usually it will be given again as that relative error in percent. So accuracy is how close you are. Precision, on the other words, describes the amount of detail in a measurement. So on your section notes, I put a little bit of extra information there under precision. So for example, if, and again, I'm looking at your section notes right now. It says a person's weight is 138.70 pounds. Is more precise than saying that the person's weight is about 140 pounds. So if we're saying about 140, then we've rounded to the nearest 10 pounds. If I did 139, now remember this is based off the 138.70. If I say 139, I rounded to the nearest 1 pound. 138.7 implies I've gone to the nearest tenths because I have 1 decimal place behind, or sorry, 1 place behind the decimal. And if it says 138.70, that implies I've measured to the nearest hundredth of a pound. So remember, tenth is 1 decimal place, hundredth is 2 decimal places, thousandth is 3 decimal places. If they are there, that implies precision. Now, it doesn't mean you're accurate. You could be way off, but at least you're precise. So let's take a look at some examples of that. All right, now this is an example I cite all the time in my class, where the Mars Climate Orbiter got sent out, and it turns out that everything it sent was wrong because people didn't double check when they were setting this up. It was two countries correlated with each other. I've not got the right word there, but 2 countries, both England and America, were working together on this project. Well, one uses pounds and the other uses kilograms. So they got this all screwed up, so everything got lost. So they spent $160 million that was wasted because somebody didn't bother to check what their unit of measure was. Excuse me. So I'm always real picky about units of measure. All right, so even though it was very precise, it was inaccurate. So very poor accuracy, but very precise information. So which one's more important? Well, you can't really say that. You just really need to have both. All right, so suppose your true weight is 102.4 pounds. The scale at the doctor's office, which can only be read to the nearest quarter pound, says you weigh 102.25 pounds. The scale at the gym, which gives a digital readout to the nearest 0.1 or nearest tenth of a pound, says you weigh 100.7 pounds. So which one is more precise and which one is more accurate? So remember, precise gives me the most decimal places. So because this one goes to the nearest tenth of a pound, the one at the gym would be the most precise. However, the scale at the doctor's office is closer to your true weight, so it's the more accurate. So the true weight's 102.4. 102.25, remember, 1/4 is 0.25. So the doctor's is saying 102.25, which is closer than the 100.7 to your actual correct weight. So even though the one at the gym is more precise, the one at the doctor's office is more accurate. So here, this is what I was referring to earlier. You need to know your true weight, but how do you actually know it? It's kind of a catch-22. So what I do is usually use the scale at the doctor's office because it it's a much more sensitive scale than the one that you jump on at the gym, but sometimes the gym's pretty good too. So how can you ever be sure? That's a conundrum that'll keep you awake at night. All right, another idea is about significant digits. You'll use this in your science class as well. So when they're talking about significant digits, it's all the digits in a number are significant except for the zeros that are included, just so you can get the decimal point in the correct place. So the number 0.001234 only has 4 significant digits, the 1, 2, 3, 4, because all those other zeros were needed to get you to the proper placement for precision. The number 1,234,000,000 still has 4 significant digits because you had to add those 6 zeros to get it into the billions place. But the number 132.0 also has 4 significant digits because that last zero was not required to get the proper placement. It's giving you the precision to the nearest tenth. So therefore, all of these numbers have 4 significant digits, but the last one, the zero, didn't have to be put in, but it was, hence that makes it significant. Tells you precision. So when we're dealing with errors, we've covered quite a bit of technical information, but it's important to understand those when you're doing measurements and errors. So let's summarize how these things all go together. All right, so these errors can occur in many ways, but they're basically classified as either random, if there's nothing we could do about it, totally unpredictable, or systematic, which happens the same way every time. So the systematic errors we can actually correct for once we know what it is. Whatever the source of the error was, its size, how big is it, can be described in 2 different ways. Absolute is just how far apart the true is from the measurement, so you'll subtract. A relative error, on the other hand, is written as a percentage. So you would do the absolute divided by the true. So those little formulas you'll need to write down and have memorized. Once you've got that measurement, we can evaluate it in terms of how accurate it was. Is it close to the true value? Or its precision, which is basically how many decimal places it has, or lack thereof. All right, so go ahead and pull out your books and look on page 56, and let's do a few more examples here. All right, so number 3 refers you to problem number 2. So you want to, again, have your book out, page 56. Look at problem number 2, and then we'll go back. So here it says a standard weight represent 1 kilogram is kept by the National Institute of Standards of Technology. All right, so we're using that 1 kilogram. So down in 3, assume you put the weight on a scale and record the weight as 1.2034278. Describe the accuracy. Well, it's not super accurate. It's 0.2 off, but it is extremely precise. Good grief. It has 1, 2, 3, 4, 5, 6, 7, 8 significant digits, and 7 of them are the precision level. I'm not even sure I can count that far back. Tens, hundreds, thousands, 10,000s, hundreds, thousands, millions, 10 millions. So yeah, extremely accurate, or sorry, extremely precise, but not very accurate because it's far off. All right, number 10. All right, here, this is just under the concepts and applications. So they're just asking you some questions, nothing more specific in the directions. So before taking off, a pilot is supposed to set the aircraft altimeter, the thing that records the elevation, to the elevation at the airport. So a pilot leaves from Denver at an altitude of 5,280 feet with her altimeter set to 2,500. Explain how this affects the altimeter reading throughout the flight, and what kind of error is this? Well, obviously her altimeter is recording high, and this would be a systematic error because it's happening consistently throughout. Actually, they're not too high, they're going to be too low because she already had it at 2,500 feet. Yeah. All right, number 11, technical specifications. So here we have our iPod battery is supposed to provide 3.7 volts. after we've done the replacement batteries, find they have a mean of 3.7, but about half of the batteries have less and half have more. Does the error appear to be random or systematic? Well, since you have some high and some low, that would be totally random. If it would be consistently the same amount off, it would be systematic, but because part are high and part are low, that would be a random error. And there's really not much you can do about that, you're just recording it. Alright, on to number 13. Here we have a new set of directions, sources of error. So for each measurement described in 13 through 20, identify at least one likely source of random error and also identify at least one likely source of systematic error. What we're doing here is looking at a situation and we're trying to think ahead about the type of errors that could be made. So when you're going to be doing a study, if you have an idea of what might happen, then you can either try to plan for it or keep an eye out for it. The random ones, you just have to keep an eye out. Once you see systematic, you can adjust it a little bit. All right, so contributions. A survey asked people for the amount of money they donate to charity in the past year. All right, now it doesn't seem like there would be too much error here, but actually there's a few we could think of. A random error could occur because people, when they make estimates, they don't really recall exactly how much. So, you've done that before. You don't remember exactly how much. You're like, well, it was about this. All right, so that would be a random error. It's going to be off for all the different people. Some might be a little high, some might be a little low. But a systematic error would occur because when estimating charity, they tend to say they donated more money than they actually did because they might want to appear to be more benevolent or more charitable. So when they estimate, they tend to estimate high. So if you were trying to figure out how much really was being donated, systematic error might say, well, let's just subtract off this much for everybody, because people tend to estimate high. And the estimations themselves are random because everybody's going to do that slightly differently. All right, how about weights of M&Ms then? Here we've got the individual M&M plain candies were obtained by placing each candy in a paper cup, then obtaining the weight without accounting for the weight of the cup. So a random error would just occur with reading the scale, like somebody might have read it incorrectly, and that's going to change from time to time, or they could be exactly correct. So a random error would just be something like reading the scale wrong or recording it wrong when you put it down on the piece of paper. The systematic error, though, is that the weight of that cup is going to be the same every time. So if you've done all the weights and you go, oh shoot, I forgot to do the cup, you can then weigh the cup and subtract that from all of the measurements you made. So systematic would be the weight of that cup was added in. All right, number 23. Here we're going to take a look at, looking for my directions, 23. Find the values of the absolute and relative error. All right, so you're going to need your calculator for this. Now we can do the absolute in our head, but the division and getting the correct decimals is a little trickier. All right, so when purchasing lunch in the cafeteria, the true value of change due is $2.75, but the incorrect amount of $1.75 was given. All right, so my absolute error, remember, is I take the measurement, which was 1.75, and I subtract my change, the true value I was given, which was 2.75, and notice you'll get a negative response. So anytime the true value is, let's see, I'm always going to do measurement minus true. So if the true is the smaller one, when I subtract, I keep saying that backwards. So my 1.75 is my measurement minus my true will give me a negative if the true value is actually higher. You'll get a positive if the true value is smaller. All right, so my absolute error is negative $1. Now I'm going to divide that by the true amount, which was 2.75. So I have negative 1 divided by 2.75. And on my calculator, that gives me negative 0.363636, repeating. So I want to move the decimal place over 2 to start with. So that would give me 36.3636. Then I round to 36.4% negative. So my answer to the absolute would be -$1, and the answer to the relative error would be -36.4%. All right, let's do that again with the baker's dozen. Here the bakery menu claims there are 12 donuts in the bag, but the baker always puts in 13. So the true amount in that bag is 13. My measurement, quote unquote, from the menu is 12. So 12, my absolute error would be 12 minus 13, or -1 donuts. And again, I'm going to do my measurement minus my true. Now, once I do that, I've got -1, and I'm going to divide it by my true value of what's in the bag, which is 13, and you should get -0.07692. That's enough decimal places, so I'm going to move it over 2 and get -7.692. So I would finally round that to -7.7%. So be careful when you're doing your rounding. Always move the decimal over 2 places, then round. Don't round first or you'll be way off. Okay, let's go on to minimizing errors. This is our last question, but it's got 4 parts. So when weighing a model 22F car battery, the measuring instrument is very precise and the weight is obtained 10 consecutive times. Okay, so all 10 measurements are not likely to be exactly the same. Thus, they will contain some sources of error. Are they systematic or random? All right, so think about that a second. All right, and the proper answer, now that you've thought about it, would be random, because somebody's just recording them. So really, some will be high, some will be low. They won't be consistently off by the same amount. So that could be a random error. Part B, if I want to minimize the effect of the random errors in determining that true weight, which is the better choice? Do I choose one of the 10 measurements, or do I report the average of all 10? All right, now here this is a great way to minimize the effect of the random errors, is to actually average it. I only want one number. But I want to randomly choose one of the 10. So if I average them, my highs and my lows will basically average out, and I'll get a fairly decent number to represent the weight of the battery. All right, so average to offset the high and the low. All right, C, describe any possible sources of systematic error in the 10 measurements. Well, if that scale is off, that will do it. So it'll be consistently off by the same amount. So I would get a systematic error if the scale is off. All right, can the process of averaging all 10 weights help reduce systematic? No, it can't. It's still going to be off no matter what. But if I know that same error is present in the average, then I could adjust for it if I knew what it was off by. So does averaging help reduce systematic? No, simply because it's always off by the same amount. Does averaging help reduce random? Yes. All right, that finishes up section 2.2, and have a good day. Thanks. Bye.